Master thermal analysis in just 30 minutes. Number 3. Feeling the heat. What can you learn with TMA? In today's webinar, you will learn the fundamentals of TMA. First, we will explain the principles of TMA. Next, we will explain TMA analysis methods. Finally, we will introduce applications using TMA. Now, let's start by reviewing the principles of TMA. Some mechanical analysis, or TMA, is defined as a technique in which a sample's temperature is subjected to a program temperature change, while the sample's change in dimension is monitored as a function of temperature or time. The measurement result of TMA is called TMA curve and is generally represented as shown in the figure. The horizontal axis represents temperature or time, and the vertical axis represents length, micrometer, or the rate of change, percentage, divided in the initial length. When the TMA curve changes upward, it means expansion of the sample. Conversely, when the TMA curve changes downward, it means the sample is shrinking. TMA measurements can determine thermal properties, such as the thermal expansion rate, coefficient of thermal expansion, CTE. Additionally, the softening temperature at which the sample softens can be also measured. The important point in TMA measurement is selecting the appropriate measurement method and attachment according to the shape of the sample. In this webinar, we will introduce 3 representative measurement methods and their corresponding attachments. First, the compression loading method, used when the sample is a self-standing solid, such as blocks or rods. A constant force, this is called the load, is applied from top to bottom on the sample during the temperature change. The second is the tensile loading method, used when the sample is a non-self-standing shape, such as film, fibers, or sheets. In this method, the load is applied from bottom to top, stretching the sample during the temperature change. The third is the penetration method, used to measure the thickness direction of plate-shaped sample. The load is applied from top to bottom while the sample is measured. The following table summarizes what can be measured with each attachment. The compression loading method and tensile loading method can determine the expansion, shrinkage, and coefficient of thermal expansion, or CTE, of the sample. Furthermore, it is possible to identify the expansion and contraction of the sample due to glass transition, crystallization, transitions involving volume changes, sintering, and other processes, as well as their temperature. By using penetration method, we can calculate the load per unit area applied to the sample, and the softening temperature of the sample under these conditions can be measured. Next, we show the TMA instrumental configuration using schematic diagrams. The figure on this slide shows schematically A differential expansion method TMA equipped with a compression loading attachment. TMA consists of, from top to bottom, a load control mechanism that controls the load applied to the sample, a differential transformer that measures changes in sample length, TMA, and a mode attachment. The sample is in contact with the core of the differential transformer via a detection rod. Furthermore, this core is connected to the load control mechanism. Because the sample, differential transformer core, and the load control mechanism are arranged in a straight line, the TMA is designed to apply a constant load to the sample. Next, let's look at the attachment in detail. In differential expansion TMA measurements, the sample and reference material, reference, are placed on the support tube of the attachment. The tips of the detection rods are brought into contact with the top of each sample. The opposite ends of the detection rods are connected to the differential transformer, the sample side to the core, and the reference side to the coil. During measurement, the support tube is enclosed by a furnace to heat and cool both the sample and reference. And the sample temperature is measured by a thermocouple installed inside the support tube. Next, we will explain the differential transformer located at the top of the attachment. The differential transformer consists of a core and coil that move independently of each other. The displacement of the core and coil is output as the TMA curve. Let's look at the movement of the differential transformer in detail. The role of the differential transformer is to output changes in the relative position of the core and coil, that is, changes in their length. For example, let the positional change be 0 when the core is at the center of the coil. After the core and coil have moved as shown in the figure on the right, the relative position has changed by delta L. If we express the displacement of the core and coil as delta L core and delta L coil representatively, then delta L equals delta L core minus delta L coil. In TMA, the differential transformer output value delta L is output of the TMA curve as the change in measurement sample length. Therefore, it is important to consider how the core and coil of the differential transformer move due to the expansion and shrinkage of the sample. Let's explain the principle of TMA measurement by focusing on the movement of the differential transformer. First, let's explain the principle of TMA measurement using the conventional single rod or non-differential expansion method where only the sample is placed on the support tube. In the conventional expansion method, a load is applied to the sample from the load control mechanism through the differential transformer and single detection rod. The coil side is fixed by a micrometer, so it does not move. Let's focus on the movement of the core and coil of the differential transformer during measurement. The displacement of the core, delta L core, corresponds to the amount of the expansion and shrinkage of the sample. It also reflects not only changes in the sample, but also the amount of the expansion and shrinkage of the detection rod, delta L detection rod, and support tube, delta L support tube, heated by the furnace. On the other hand, the displacement of the fixed coil, delta L coil, is 0. The TMA output value, that is, the differential transformer output value, delta L TMA, is expressed as the difference between the delta L core and coil. In the conventional expansion method, delta L TMA equals the delta L core and is expressed as the sum of the delta L sample, detection rod, and support tube. When the change due to thermal expansion or shrinkage of the sample is large enough to be negligible the change in the detection rod and support tube, delta L TMA can be regarded as the expansion or shrinkage value of the sample. On the other hand, when measuring low thermal expansion or shrinkage materials or small-sized samples, that is, when the change in the sample is very small and changes in the detection rod and support tube cannot be neglected, what should be done? As mentioned in the previous slide, when you want to accurately measure minute changes in the sample, using a differential expansion method is an effective method. In the differential expansion method, quartz or alumina, whose thermal expansions are known, are used as a reference material. Reference. The reference is placed on a support tube similar to the measurement sample, and the detection rod in contact with the reference is connected to the coil of the differential transformer. The key point in the differential expansion method is that a material with a known thermal expansion is used as the reference. Let's check the differences in core and coil displacement configurations during TMA measurement. The delta L core in the differential expansion method is the same as that of conventional expansion method, expressed as the sum of the delta L sample, detection rod, and support tube. On the other hand, in this configuration as well, the expansion or shrinkage of the reference, detection rod, and support tube also occur on the coil side, so that displacement of the delta L coil is expressed as the sum of displacement of the delta L reference, detection rod, and support tube. In the measurement, the detection rod for a sample and reference are made of the same material. Furthermore, the sample and reference are placed on the same support tube. Therefore, when calculating delta L TMA, the delta L detection rod and support tube can be cancelled out. Ultimately, delta L TMA can be expressed as the difference between the delta L sample and reference. Further, rearranging the equation, delta L sample can be expressed as the sum of delta L TMA and delta L reference. Here, since the summer expansion rate of the reference is known, the expansion amount of the reference at each temperature, i.e., the displacement, can be calculated. This is called reference collection value. In the differential expansion method, delta L sample can be determined from delta L TMA and delta L reference obtained through reference collection value. Consequently, compared to the conventional expansion method with single rod, this method allows for more accurate measurement of low thermal expansion materials and small size samples. In the slides so far, we have explained the TMA instrument and measurement principle. Next, we will explain how to analyze the TMA curve. TMA curve can be analyzed the temperatures at which the material's mechanical properties can be evaluated. For analysis of softening temperature and deformation point, the temperature at which sample expansion reverses shrinkage is analyzed. As shown by number 1 in the figure, the temperature may be read at the peak, upper figure, or at the intersection of tangent lines for the expansion and shrinkage reason, lower figure. Also, as shown by number 2 in the figure, the temperature at which a change in expansion rate occurs can be determined as an extrapolated temperature. This is obtained by drawing tangent lines at the maximum slope before and after the change in expansion rate and analyzing their intersection temperature. As the main analysis of TMA, the sample's thermal properties, thermal expansion rate E, and mean coefficient of thermal expansion CTE alpha bar are calculated. Let L0 be the initial length of the sample at starting temperature, L1 be the sample length at reference temperature T1, and L2 be the sample length at the arbitrary temperature T2, at which the thermal properties are determined. The thermal expansion rate represents the percentage of expansion that occurs between the reference temperature and any given temperature. The expansion rate is calculated as a percentage by dividing the difference in sample length from the reference temperature L2 minus L1 by the initial length L0. The mean coefficient of thermal expansion CTE represents how much the sample expands or shrinks per unit temperature. CTE is equal to the expansion rate before converting to percentage divided by the temperature difference T2 minus T1. Note that the thermal expansion rate and CTE changes their calculated value at T2 depending on the reference temperature T1. Now, let's take a look at some examples of TMA applications in the following slide. First, we will present a case study of glass measurement taken using the compression loading method. When the solid glass sample was heated from 25 degrees Celsius, An upward change was observed, indicating the expansion occurred. Further heating reveals a rapid increase in the expansion rate beyond a certain temperature, and with further heating, a downward change, shrinkage, was observed. The extrapolated temperature, representing the temperature at which the expansion rate changes, was analyzed to be 290 degrees Celsius. The softening temperature at which expansion turns to shrinkage was 309 degrees Celsius. Next, let's calculate the expansion rate and mean coefficient of expansion for the glass. This time, we will use a reference temperature of 50 degrees Celsius for the calculation. The initial length of the sample is 15.14 millimeters. The amount of thermal expansion at 50, 100, 150, and 200 degrees Celsius can be analyzed from the TMA curve. From these values, the expansion rate and CTE of the sample at which temperature were calculated, and the results were summarized in the table. Next is an example of measurements taken on a polytetrafluoroethylene PTFE seed. We used the compression loading method to measure the dimensional changes in the thickness direction of the sample over a temperature range of minus 50 degrees Celsius to 200 degrees Celsius. The TMA curve shows an upward change, indicating expansion of PTFE due to heating. Furthermore, the expansion rate and CTE at 100, 150, and 200 degrees Celsius with a reference temperature of 50 degrees Celsius were determined as shown in the table. The CTE of PTFE is one order of magnitude larger than that of the glass shown, indicating that PTFE exhibits greater shape changes with temperature variation. Also, the TMA curve for PTFE shows a rapid increase in expansion rate of approximately 1% between 20 degrees Celsius and 25 degrees Celsius. This phenomenon is due to a volume change associated with the crystal transition of PTFE, and TMA can detect volume changes associated with the reaction of the sample. These results show that the expansion rate is significantly higher near room temperature. This means that PTFE requires careful handling near room temperature with regards to its shape. Next, we present an example of TMA measurement using the tensile loading method. The measurements were performed on samples cut from PET film in two different directions. The expansion rate of samples cut length direction, direction A, and width direction, direction B, from the same film were compared. While direction A shows expansion, direction B shows shrinkage from around 100 degrees Celsius. This is likely due to the film being stretched in the B direction during its production. As such, for stretched film, The expansion rate and behavior may differ depending on the direction in which the sample is cut. Finally, we introduce a measurement example using the penetration method. In this case, the softening temperature of amorphous PET was measured. Look at the TMA curve. Amorphous PET began to shrink around 70 degrees Celsius, followed by a sharp increase in the shrinkage rate. Observe the sample softening. The softening temperature analyzed from the extrapolated temperature is 86 degrees Celsius. An important point about the penetration method is that the resulting softening temperature depends on the load per unit area applied to the sample. In this measurement, a load of 500 mN was applied, using a pin tip with a diameter of 0.5 mm. This means the load per unit area is approximately 2.5 MPa, and the softening temperature under this condition is 86 degrees Celsius. Here is a summary of this webinar. TMA measurement is a technique for measuring shape changes in dimension. Depending on the sample shape and purpose, the compression loading method, tension loading method, or penetration method is selected. There are two approaches: the conventional single load expansion method, which measures only the sample, and the differential expansion method, which measures sample alongside a reference material. When the volume change accompanies a reaction in the sample, the change in expansion rate can be determined as an extrapolated temperature. From TMA measurement results, the some physical properties, expansion rate and mean coefficient thermal expansion, can be determined. Our TMA 8311 can be used as a standalone when you can measure from room temperature up to maximum 1500 degrees Celsius. It can also be connected to a cooling unit, such as the refrigerated cooling unit, from measurement ranges from -70 degrees Celsius to 600 degrees Celsius, and the oat-filling liquid nitrogen unit for measurements ranging from -150 degrees Celsius to 600 degrees Celsius. We can also run measurements under humidity-controlled atmosphere conditions of room temperature to 85 degrees Celsius and 5% to 90% RH. So, thank you for listening this webinar.